So this is a multi-component, meaning many species can be treated, numerical reactive transport model that you can utilize for a wide variety of different applications. You might have heard it called Crunch Flow, or you might have heard it called Crunch Taupe. Sorry about that. That was me. So this is a very complicated slide that says that this model is very simple. And the basic idea is that it's a continuum scale reactive transport simulation, meaning that each one of these grid cells is attached to the adjacent or neighboring grid cells, and within each grid cell, every parameter is an average. Parameters like permeability, porosity, the volume of minerals, the amount of fluid, the solutes, and we then move some of those solutes and fluids into the adjacent grid cells. This causes those grid cells to be out of chemical equilibrium, and so we have to solve reactions. And inside of this one innocent-looking little term is a ton of different kinds of reactions that we can consider. Just simple equilibrium, absorption of mineral surfaces, biologically mediated reactions, reactions that cause precipitation of minerals, dissolution of minerals. It's exciting. It's kind of limitless in a way. And so just to give you a sense of the scope, what Crunch Taupe does is handle multi-dimensional fluid flow and solute transport. To some extent, we can do multi-phase. We can diffuse gases. We can definitely advect and diffuse fluids. We can do a huge variety of multi-component chemical systems. And we can mix together both kinetic and equilibrium reaction networks. And we use it for all kinds of different applications like weathering reactions, carbon storage. I mentioned already these biologically mediated reactions, which is really a lot of fun. Kind of a new area that we're moving into now is soil profile development and terrestrial weathering. And of course, this all comes originally from sort of the classic hydrologic contaminant transport. If you want to play with Crunch, you're going to be staring at things like this for the next few days. So these are examples of input files that you basically build, and that allows you to read this into the software. The software gives you back output files, and you get to figure out how to plot them. And once you've got one of these things running, you get to look at all sorts of different processes. So here are just a couple of examples. In this case, we're looking at the difference in how ions diffuse across some distance when all we consider is chemical gradients versus when we consider both chemical and charge gradients, which is kind of fun. And a second example is a 2D simulation in which we are flowing, over here, we're flowing an acidic fluid with a lot of sulfate in it across this system. We're dissolving out calcite, and we're replacing it with gypsum. And as you might be able to see, there's actual physical structure involved in here too. So we've read in a heterogeneous permeability, and it's causing these really interesting replacement reactions. So if you're interested in learning more about this, or maybe developing a little example of your own, I'd be happy to help out. So thank you.